Good evening, viewer. Welcome to our Glory Globe TV. Here's the most amazing news for our viewers. Researchers from the Harvard John A. Paulson School of Engineering and Applied Sciences, Harvard Department of Chemistry and Chemical Biology, and Urchet University have reported on a previously elusive way to improve the selectivity of catalytic reactions, adding a new method of increasing the efficacy of catalyst for a potentially wide various industries including pharmaceuticals, cosmetics and much more. Research will be published February 16 in Nature Catalysis. The chemical industry relies on catalyst for over 90% of its processes, and nearly all these catalysts consist of nanoparticles dispersed on top of a substrate. Researchers have long suspected that the size of individual nanoparticles and the distance between them play important roles in the speed of and the products produced in the catalytic reactions. But because nanoparticles are prone to moving around and agglomerating during catalysis, it has been difficult to study exactly how. Over the past decade, Zona Eisenberg, the Amy Smith Berylson Professor of Materials Science and Professor of Chemistry and Chemical Biology, and her lab have been drawing inspiration from nature to build highly ordered porous materials for a wide range of catalytic reactions. Inspired by the structure of butterfly wings, the researchers designed a new catalyst platform that partially embeds nanoparticles into the substrate, trapping them to and also they don't move around during catalysis while leaving the rest of the nanoparticles surface exposed, enabling them to perform the catalytic reactions efficiently and without agglomeration. Researchers found that the distance between particles had a huge impact on the selectivity of the reaction. Many industrially relevant chemical reactions follow a cascade whereby chemical A is turned to chemical B, which can then be turned into chemical C, and so forth, said Kang Ruhi Garik Lim, a graduate student in the Eisenberg lab and first author of the study. In some catalytic processes, the intermediate chemical B, is the goal, while in another it is the end product, chemical C. The selectivity of the catalyst refers to whether it favors the production of chemical B or chemical C. A good example of this is the production of benzyl alcohol, a chemical used in everything from Celacas paints and leather productions to intravenous medications, cosmetics and topical drugs. Benzyl alcohol is the intermediate chemical B derived from the hydrogenation of benzaldehyde before the reaction creates toluene, chemical C, another commonly used chemical but of lower value. In order to produce benzyl alcohol efficiently, the formation of toluene needs to be suppressed. Behind the report, Glory Globe TV, Delhi, Bharat.